What you're watching right now is a simulation of vehicle steering and yaw motion. You turn the steering wheel and the car turns. It seems like common sense. But I want to ask you a question. Why does the car actually turn? Is it simply because the front wheels are angled, guiding the car? That fits our intuition, but that logic only holds true at very low speeds. For the vast majority of driving scenarios, we need to rethink this in terms of forces. To quantify these forces, we need to simplify the complex vehicle structure into a mathematical model suitable for engineering. In this video, you will master the 2 degree of freedom bicycle model. This model is the absolute cornerstone for autonomous path tracking and chassis control. As always, the simulation code is free to download in the description below. Welcome to MetaLogic. When a vehicle travels in a circle, it is subjected to centrifugal force. Balancing this force is the tire's cornering force. Let's take a closer look at the parameters. Cg is the location of the center of gravity. Beta represents the vehicle side slip angle at the Cg. The letter R is the vehicle's yaw rate. I stands for the yaw moment of inertia, and Kf and Kr represent the cornering stiffness of the front and rear tires, respectively. However, using a full model to analyze yaw motion is overly complex, so we simplify it further. We keep the Cg positions unchanged, but we merge the left and right wheels together. Consequently, the front and rear cornering stiffness become 2 times Kf and 2 times Kr. All other parameters remain the same. This transformation turns the 4-wheel model into a 2-wheel model. Since it resembles a bicycle, it is formally known as the 2 degree of freedom bicycle model. So, what exactly is tire cornering stiffness? Let's examine what happens to the front wheel during a turn. When you turn the steering wheel, you get a tire steering angle, delta. The side slip angle at the front of the vehicle body is beta f. Therefore, delta minus beta f is the equivalent slip angle of the front wheel. This slip angle causes the tire's contact patch to deform against the ground, which generates lateral cornering force. If we look at this graph, the horizontal axis represents the slip angle, alpha f. The vertical axis represents the cornering force, Cf. The slope formed by the cornering force relative to the slip angle is defined as the cornering stiffness. By adding in the front and rear wheelbase dimensions, the force analysis for this 2 degree of freedom bicycle model is now complete. It is typically applied to analyze yaw response, or for autonomous lane-keeping systems. When a vehicle travels in a circle, the lateral acceleration AY is composed of 2 parts, circular motion and translational motion. First, the acceleration from circular motion is v squared divided by r, which simplifies to v times the yaw rate r. Second, let's look at the acceleration from translational motion. The lateral velocity derivative v dot equals v times the derivative of sine beta. Using the chain rule, this becomes v times beta dot times cosine beta. Since the side slip angle is usually small, cosine beta is approximately equal to 1. Therefore, v dot is approximately v times beta dot. Finally, by combining the circular and the translational components, the total lateral acceleration AY equals v times r plus beta dot. In this way, we have established the relationship between lateral acceleration and the side slip angle. Now, let's analyze the relationship between the front axle slip angle and the side slip angle at the center of gravity when the vehicle travels in a circle. If we initially ignore the vehicle's yaw angle, the arc swept by the CG can be approximated as a triangle. Geometrically, this creates an angle of LF. divided by r. Next, let's assume the wheels are fixed and at the body side slip angle beta. Therefore, the actual front axle slip angle beta f equals beta plus LF divided by r. Since the yaw rate r equals v divided by r, we can substitute this into the equation. Beta f equals beta plus LF times r divided by v by the same logic for the rear wheels. Beta r equals beta minus LR times r divided by v. In this way, we have successfully established the relationships between beta r, beta f, and beta r. Now, let's establish the kinematic equations for the 2-degree of freedom model. Before we start, please note that in these equations, FF and FR represent the lateral forces of the front and rear wheels. First, the lateral force balance, M times AY equals 2 times FF plus the 2 times FR. Expanding the acceleration term, mv times r plus beta dot equals the sum of the tire forces. Next, the yaw moment balance, Iz times r dot equals 2LF times FF minus 2LR times FR. Now, we define the tire forces. Note the negative sign for stiffness. For the front axle, AF equals negative KF times beta F minus delta, where beta F is defined as beta plus LF times R divided by V. For the rear axle, if R equals negative KR times beta R, where beta R is defined as beta minus LR times R divided by V. Next, let's use the 2-degree of freedom bicycle model to calculate the vehicle's yaw rate gain. The table shown here lists the specific vehicle parameters used in this calculation. Regarding the yaw rate gain results, in engineering, we focus on the following key metrics to evaluate the vehicle's response and convergence. First, the peak gain is 15.6 decibels, and the peak frequency is 0.8 Hz. Generally, a higher peak frequency value indicates a better vehicle yaw response. Next, at a frequency near zero, we find the vehicle's steady state gain. The difference between this value and the peak gain is used to evaluate the vehicle's convergence. The smaller this difference is, the larger the system's damping ratio, and consequently, the better the convergence. That wraps up the main content for this episode. Although this model seems simple, it is the fundamental basis for the entire field of vehicle dynamics, chassis control, and autonomous driving. The source code is available in the description below. If you have any questions, feel free to leave a comment. See you in the next video.